All right, go ahead and have your homework out if you would, please. Books open to page 142, and you answer 5 questions. Questions 1, 2, 3, 7, and 8. Question 1 says, how can a force vector be represented, Michael?
A force vector can be represented as an arrow.
Very good. Number 2, what is included in a free body diagram, Kendall?
Included in a free body diagram is the object, which can be represented by the dot or spots, and then the forces, which are drawn as arrows.
Good, all the forces. Any force that is possibly acting on the object needs to be included. Number 3, under what condition will an object accelerate, Audrey?
Under the condition that force may be applied anywhere with no effect, that object is accelerated.
Michael, what do you have?
An object will accelerate under the condition of a force pushing or pulling it.
If you added one word to your answer, you'd be right. Kendall?
An object will accelerate under the condition when net force acts upon it.
If a net force acts upon it. Meaning, if a force acts this way, but another force acts this way, and they cancel, then it doesn't accelerate. But if there is a net force, meaning one force wins, as long as some force actually wins, then yes, an object will accelerate. So as long as the forces don't cancel, if the sum of the forces in the x is greater than 0, if there is a net force present, is kind of what we were going for there. Number 7, what are concurrent forces and the resultant force? Back to Michael.
Concurrent forces are two forces acting upon an object at the same time. The resultant force is the outcome of all other forces.
All right, number 8, why is it easier to move a chair across the floor by pulling at an upward angle than by pushing? Audrey?
It's easier to move a chair across the floor by pulling at an upward angle than by pushing because of friction and level surface.
Okay, yeah, friction. Does anyone have anything else to add on that? It does have to do with friction, but why would the friction be any different? I mean, it's the same chair, right? So why would pulling like this make any less friction than that?
It reduces the normal force.
Right. So the idea is the chair weighs the same regardless, but if you push, inevitably when you push, unless you get directly behind it, like that, here I don't believe, and I don't know if the camera can see any of this, but if I'm pushing, I'm down on the floor pushing exactly horizontal, I'm not pushing down at all. But assuming I'm standing up, when I push, notice my arms are down and forward, right? I'm pushing forward, but I'm also bearing down, which adds to the weight. Meaning now the ground is pushing up on the desk, both to compensate for the desk's weight and my force, whatever component of my force is downward. I'm actually increasing the friction by pushing downward. But when I lift upward, again, if I pull perfectly horizontal, I'm not doing anything. But if I'm lifting slightly upward, which is more normal, and even if I'm not lifting it up off the ground, right? Even just lifting like this, I'm minimizing the amount of weight by supporting at least some of it. Not enough to lift it off the ground, but supporting some of it, right? And by supporting some of the weight, that's less weight for the ground to push up against, less normal force, less friction force. So it all does come back to friction, but the key is what is the normal force doing, or rather, what am I doing to affect the normal force? Good. Speaking of which, let's go and work a problem. And this problem for us in the South, y'all know what a sled is? You probably read about it in books. Okay, you were up north at some point. Anyone ever actually been on a sled? Okay, so you are true Georgia Southern girl, never been on a sled. Okay, basically, you know what a sled is though. Okay. All right, so anyway, a sled, like, you tug it up to the top of the hill, get on it, woo, down the hill. It's like a slide, except you don't need a slide. The whole hill is your slide. All right, anyway, so there's this boy, and he's got a 28-kilogram sled. And of course, when you get sled, and you got the runners of the sled, and probably supported by some triangular braces, because a triangle is a shape of strength, right, Michael? As we talked about in geometry just a few days ago. And boy, even a little boy is taller than sled. So little boy isn't going to grab the sled down here and pull it along with him. Instead, there's going to be a rope that he's going to attach to the front of the sled. He's going to drag it by the rope, right? That's how you pull a sled up the hill. Well, as he's pulling, though, realize, is he pulling up or is he pulling forward? Yes. Okay, so his rope is going to be angled at a 25-degree angle. So we have a 25-degree angled rope. He exerts a force of 50 newtons. Now, he's not made it to the hill yet, okay? He doesn't live on a hill. He lives near a hill. So he's trudging, that's a great word, trudging down the street, dragging his sled behind him to the hill. So he's on level ground right now, because we haven't talked about how to do slope surfaces yet. We'll get there later. But he's got a 28 kilogram sled, pulling it by a 25-degree angle rope, that's 25 above the horizontal, and he's applying 50 newtons of force. Now, the icy, snowy ground and those nice, polished runners of the sled have a very low coefficient of friction. We'll say that mu sub k is 0.103. The question is, what is the acceleration of the sled? First thing we do in any force problem is draw a sketch that we call, class, a
Free
body diagram. Okay, so how should we draw the sled?
Box.
Box? All right, very good. That is the sled. Because artwork like that is just too hard for a scientist. All right? Now, the upside of a box for the sled is that you can write inside the box. A dot gives you nowhere to write. I want to go ahead and write inside my box real small, 28 kilograms. I'm going to go and write inside the box 28 kilograms. That's the mass of the sled. That's a number that I'm going to come back to later. All right, now, in addition to drawing the object, class, I have to draw all of the forces. What's one force acting on the sled?
Weight.
The weight of the sled is bearing straight downward. What other forces do we have? Normal force is holding the sled up. Because that'd be really traumatic if he gets his brand new sled out. It's like, oh boy, Merry Christmas, thank you, Daddy. He gets his sled out, goes outside. As soon as he sets the sled down, it starts sinking into the ground. Traumatic, okay? Single. Normal force is acting upward. What other forces? Friction force is resisting the boy. So now, which way do you want the boy to go, Kendall? You want to go right or go left? He goes right, okay? And so the boy is going right, which means friction is acting against the boy this way. All right? And there's one more force, pretty obvious.
Newtons.
Well, force is measured in newtons, but
Applied force.
the applied force, the boy, right? The fact that the only reason the sled moves at all, right? If not for the boy, I mean, there is friction present, right, if the sled is just sitting there, but it's not acting on the sled. It's there waiting to act, but it's not acting on the sled if the sled's not moving. But he starts moving the sled. Now, his force is not in the x, and it is not in the y. It's at an angle. That's the applied force. But because it is neither in the x nor in the y, it is both in the x and in the y at the same time. At least a component of it is. So we have some applied force in the x, and we have some applied force in the y. By drawing these two components, class, I've made a nice little, specifically a right triangle, with a 25-degree angle right here. And where I have right triangles, I can use trig ratios, sine, cosine, and tangent. Now again, it's important to remember that this is the actual applied force. We know the applied force, class, is 50 point newtons. All right? We need to figure out how much of the applied force is in the x, how much of the applied force is in the y. And you want to put these in the memories of your calculator. All right, give me one of the components, Audrey.
The x is 25.376.
Ooh, that is not what I think you might have it backwards. Remember, cosine is adjacent over hypotenuse, so you're going to use cosine for the x and sine for the y. No, I didn't get that for either of them, though. You said 25?
Yeah.
That's not what I got. Is your calculator degree mode? Okay. Do the same thing again?
Yeah.
It's
Okay.
just multiplying it by 28.
28. Okay, so we'd have to take the...
Yeah, I was
You were multiplying by 28, okay. Yeah, so the 50 is the hypotenuse, right? The 28 kilograms, that's the mass of this, but the 50 is the hypotenuse. Thank you, you can call Michael. So we're going to take the 50 times the cosine of 25 to get...
45.3.
So even though he's not actually pulling horizontally, there are 45 newtons of force that pull forward on the sled. What about the upward component? And I put this in memory 1. Kendall?
21.130.
And I put that in memory 2. All right, did you get both components, Michael? And Audrey have them now. All right. Now then, we need to find the other forces. So all of this cluster, I found everything. The real applied force I was given, I found the X, I found the Y. What's the next force I should find? Should I find the friction force next?
Let's find the weight next.
I can't find the friction force, can I, class? Because in order to know the friction force, you have to know the normal force. Or should I find the normal force next? Well, you don't know the normal force until you know the weight. So weight is a great place to start. How do I find weight, Michael?
It tells you 28 kilograms.
Ooh,
Oh,
careful.
weight,
Is that weight?
yeah.
That's mass. How do I find weight?
That times 9.80.
Yeah, mass times gravity. There we go. So we'll take the 28 times the 9.80. And what is the weight of this boy's sled? Michael?
274.4.
I don't need a memory for that, I don't think. All right, that's a 4. It just looks funny. I'm not sure what happened there. That's a 274.4. All right, now, normally, if the boy were not doing anything to the sled, class, if the weight is 274.4 newtons on level ground, then the normal force is going to be,
274.4.
but then there's the boy, and the boy messes with the math a little bit. Is the boy going to increase the normal force or decrease the normal force here, class? Decrease. What could the boy do to increase the normal force?
Pull it down.
Okay, he could pull it at a downward angle, or he could sit on the sled. That would increase the normal force, wouldn't it? Because now you have more weight, right? But by lifting slightly upward, not lifting the sled, I mean, he's only 21 newtons are going up, right? It's a 274 newton sled. That sled is not coming off the ground with only 21 newtons. But it is helping the ground out, because the ground now only has to apply, Audrey, the upward normal force only has to be Kendall? Michael?
253.269.
253.269, blah, blah, blah. Now, Michael, how did you get that? Because the girls seem a little confused. How did you get 253.26?
I subtracted the weight minus the upward force.
You realize the weight is down. You're looking for what force goes up or down already. Well, notice there are 2 upward forces. Normal force is up, and that force is up. You see, there's 2 ups countering a single down. Does that make sense? So, for instance, let's suppose Audrey and Kendall decided we are going to lift Michael up in the air like an exalted leader, or cheerleading mountain, whatever. And they're like, we're going to lift Michael. Now, Kendall on her own is not getting Michael off the ground. Audrey on her own is not getting Michael off the ground. I have my doubts if the 2 of them together can get Michael off the ground. We're not going to test this, but perhaps let's just say, for sake of argument, that Audrey is really strong. Like, she looks all sweet and innocent. She's a muscle woman, okay? Like, see her throw a softball, she can throw. All right, and then Kendall's smaller, okay? So we have this little bitty bit of help. But because there's this little bitty bit of Kendall help, Audrey is able to take care of the rest of Michael. So does that kind of give you the idea of what we're doing here? The sled weighs this, but instead of the ground on its own holding up the whole sled, all 274.4 newtons, the upward, whatever the boy's doing, just helps out that little bit, makes it easier on the ground. Does that make sense? That's already. So we subtract memory 2, in my case, or whatever memory you used, from that weight bearing downward. That's the normal force now. By pulling on the rope upward at an angle, he's diminished normal force, which is going to, in turn, class, diminish the friction force. How do I find friction force? Back to Audrey. Good, coefficient times normal force. Well, the coefficient here is the 0.103, and we have the friction force on our calculator right now. Should, right? The 253, everybody's got that down the calculator now, so we multiply that by the 0.103. How much friction force is there, class?
26.086.
And I'll go and put this in memory 3. Now I want you to notice that the pink vectors, the vertical vectors, the y components, all cancel. When all the forces cancel in a particular direction, we have translational equilibrium. That means there's no acceleration, meaning it doesn't suddenly start rising or suddenly start sinking. Horizontally, we have two forces. I have this force forward, and I have this force backward. Do I have translational equilibrium in the x? No, because the forces do not cancel out. They do not balance each other. They are not equal. Instead, we have a clear winner. Who wins? The boy, the applied force in the x, right? And that's important, because otherwise it'd be really defeating for the little boy. I can't get it to move. Oh yeah, sorry, son, I've got it tied to the Porsche rail. You know, whatever. So anyway, since there is a clear winner, then there is what we call a net force, or a sum of the forces in the x. Now we say sum, which means you add. Well, we would, because since friction is against the motion, class, we could say friction is a negative force. Practically speaking, just subtract them, because that's the same as adding a negative. So we'll take the recall 1 minus the recall 3, and what is the net force, or what we call the sum of the forces in the x?
19.22.
It's as if this object has no other forces acting on it but a single 19.22 force acting that way. Now, there are all the other forces, but the resultant force is 19.22 that way. If that's the net force, and I want to find acceleration, remember F equals ma, well, more accurately, the sum of the forces in the x equals ma. So to find a, I need to divide out the mass from both sides, and that will give me the acceleration. Take the sum of the forces in the x, which you should have on your calculator, and this is why I like having this number here in the picture, so it's just there for reference. Divide out the mass of 28, and how rapidly is this boy accelerating forward with his sled in tow?
6, 8, 6, 7.
Okay, and round it off just 2 sig figs, right? Looking at the given numbers. So we'll say
0.67.
meters per second squared. And there we go. Questions on this? All right, take a look in your textbooks if you would please now. At page 142, and Kendall's still there, page 142. Now let's look at a couple of problems. These aren't going to be complete force problems, just to help give us an idea of how this angled forces, finding the components, stuff like that is going to work out. All right, so page 142. We'll read problem number 4, if you would please, Michael.
When a man pushes his lawnmower, he applies a force of 200 newtons at 45 degrees below the horizontal. What is the magnitude of the downward force that is added to the weight of the mower?
All right, so we have lawnmower, and there's handle on lawnmower. Okay, that's a lawnmower. Okay, and this is a man pushing lawnmower. He does it without his hands touching the handle, by the way. I just wanted to point that out. He's special. He uses the force. Well, anyway, if he is pushing on the handle, assuming he's pushing horizontally, the handle is going where, class? Downward. So even though his force may be forward, that force is transmitted here, and so the force actually goes down at an angle, even though he's maybe not intending for it to. So here's the question. Is he pushing forward or is he pushing downward? Yes, he's pushing both. Some of his force is forward, some of his force is downward. It says that the handle's angled how, Michael?
45 degrees.
45 degrees. So it doesn't matter whether I look at it 45 above the horizontal, 45 below the horizontal, 45 to the vertical. 45 is just going to be 45. And he pushes with how much force?
210 newtons.
210 newtons. So now, free body diagram, that's the lawnmower. You like my artwork? Lawnmower. There's a 45 degree angle here, or you could say it's here. Perhaps the better way to look at it is here, because this is the point at which the force is being applied. Some of the force is forward, some of the force is downward. The applied force, it says, was, you say it one more time?
210 newtons.
210 newtons at this angle. Some of the 210 newtons is applied in the X, some of the 210 newtons is applied in the Y. At your seats, well, first of all, if it's a 45, 45, 90, what do we know about those two components?
Sides are 1.
They're going to be equal, aren't they? Right? So they're going to be the same. So we could, now Michael's thinking, divide by square root of 2. Or you could use sine or cosine. Either way works. If we did use sine, class, that would be for which of these components?
FAY.
The f sub ay. And if we wanted to find use cosine, that would be for the f sub ax. Again, they're going to be the same either way, so really you kind of only have to do it once. We'll take the sine or the cosine of 45, multiply by 210, or divide by the square root of 2. There's a number of ways to approach it since it's a special triangle. And what is the applied force in both the x and y class?
148.492.
Now, does it tell me how much the lawnmower weighs? No. It's really inconsequential, right? There is, of course, going to be a force of weight, correct? There is also going to be a normal force. Now, here's the question. I don't know how much this thing weighs. What will happen to the normal force, though? Increase by how much? 148.49. Because whatever the weight is, on top of that weight, we have an additional 148.49. The ground is now supporting both the weight and the applied in the y. What's that going to do if we increase the normal force? Increase the friction force, which means it's a good thing it's on wheels. Right? We really don't care if we increase the friction force because it's rolling anyway. Who cares, right? There's minimal friction anyway since it's on wheels, which is why we don't care that it's inefficient to push. But if it were something you had on the ground sliding across the ground, that would be highly inefficient. We don't really care. We're rolling it anyway. The answer to the question that by how much or how much force, what is the magnitude of the downward force that's added to the weight of the mower? That's this right here, rounded off to, how many sig figs, class?
2.
Looking at the actual problem, 3. Yeah, I forgot to write 0.0 and point at the end of these. 3 sig figs, so we'll say it adds 148 newtons, 3 sig figs. 148 newtons to the weight of the mower. So if the mower was a 300 newton mower, it now has an apparent weight, as far as the ground is concerned, of 448 newtons. Make sense? Look at number 5. Go to read that for us, Audrey.
A guy wire on a billboard makes an angle of 40 degrees with the ground. If it has a tension of 483 pounds, how much force lives straight up on anchorage?
Now, do y'all know what guy wires are? Okay. You know, right outside the church here, there's a telephone pole, and then there's this wiry thing that comes down. There's a little yellow sheath on it to keep you from strangling yourself. That's a guy wire. Basically, it's to keep the pole from falling over. So on a telephone pole, right, you've got wires that come here, that come here. Well, if there's also a wire that goes across the street that way, you've got wires that are pulling both ways this way, they cancel out, and a wire pulling this way across the street toward the parking lot, and there are no wires coming back this way. So what they'll do is they'll put a wire down to the ground, a cable down to the ground to hold it in place so that way we don't get the toppling over effect. However, I've seen that on telephone poles. I've seen that on cell phone towers. I've seen it on radio towers. I've never seen a guy wire on a billboard. You ever seen one on a billboard? No. So we're going to change this problem. It's not a billboard, it's a cell phone tower. All right? Cell phone tower. You know, you got all the little crisscrossy X-looking thingies to make triangles because it's a shape of strength. And usually, by the way, they'll have a few different guy wires anchored down on each side. And if you were to look at it from above, there's usually a triangular shape to it. And I'll have guy wires coming out here guy wire is coming out here, and guy wire is coming out here at 120-degree angles to each other. So in all three directions, it's anchored down. Now, as you get to the base, usually there is a block of concrete that is sunk down into the ground, and then the anchor is attached into that. Not the case with our telephone pole, right? Our telephone pole or power pole right beside the church, it's just an anchor that they screw into the ground and they hope the ground can hold it. But for these larger towers, they actually have a block of cement that holds the anchorage there. Here's the thought. As the guy wire is applied right here, is the guy wire pulling up or is it pulling forward? Yes. The guy wire is pulling this way, right? There's a tension pulling this way. That means it is lifting up and it is pulling forward. Now, ground is going to stop it from going forward, correct? What's to stop it from coming up out of the ground? The sheer weight of the block of cement. Okay, so that's the reason for the block of cement. Now here, they may not have as much tension in the guy wire on the telephone pole. Maybe they figure if I take this anchorage and I screw it into the ground, it's a wide, whatever that thing is called, the, you know what I'm talking about, the part that goes around, okay, that part is usually a little bit wider, so as they screw it down into the ground, it grabs the ground really well. You even know this for volleyball, for PE, right? We don't have a screw, we don't have anchorage, we just have the stakes that we pound down. I pound them in not straight down though. Pound them in an angle. Because what's going to happen with that? It's going to pull in. Well, I'm not worried about that. It's not going anywhere. But it's going to lift up. And if I pound it straight down, the upward force could lift it straight back up out of the ground. So I always pound them at an angle. Anyway, back to Audrey's point. This guy wire makes a 40-degree angle to the ground. And it says there's tension. Remember we said tension force is force that's transmitted through a wire, connector of some kind, cable, string, chain, rope, whatever, something like that. We've got tension in this guy wire, and you said it was how much tension? 4,000 pounds of tension on this cable. Again, some of that tension would try to slide the block of cement through the ground, but the ground isn't going to give. Some of that is lifting up. The question is how much? Well, remember we talked about the principle of transmissibility. It doesn't matter where I put this vector, as long as this vector is what it is. You realize I could put this vector right here. Same vector, correct? So if I put the vector here, this right here, class, is the, this here is the opposite from this angle, and this here is the hypotenuse. So what trig function would I use? Sine. Another way to look at it would be this. If it's lifting at an angle, it's lifting up and it's lifting forward, and if this is a 40-degree angle, this is a 40-degree angle, and still it's the opposite. Okay, so there's a couple ways you could draw it. So we need the opposite over a hypotenuse. The sine of our 40-degree angle equals opposite over the 4,000. And how much upward force is there? How much force is going to lift up on the anchorage?
2,571.
All right, so over 2,500 pounds lifting upward. How much? Is it 3 sig figs? So we'll say 2,570 pounds is the tension in the Y. Here's the tension. There's tension in the X and there's tension in the Y. 2,570 pounds of tension in the Y, which means we better make sure this block of concrete weighs at least 2,570 pounds, or else slowly, little by little, it's going to come up. And if it comes up at any at all, this guy wire is going to start to develop a little bit of slack. And we don't want slack in the guy wire because then the tower begins to get slack. And then the tower, boom, and nobody has cell phone coverage. Everybody screams at the cell phone company. Okay? Anyway, questions on this. Do we see how to work with angled forces? Find the X and Y components. Let's take a look at a problem here on the screen. And I'm going to widen that out just a little bit. All right, so give it just a second to come up here. Again, we weren't finding all of the forces necessarily at play. All right. Now this problem, as it's coming up, any of you ever been to the Bill Rice Ranch, Tennessee? Okay. I went there a couple of years when I was in high school. That was our summer camp, and then I started doing lawn jobs and didn't have time to go. But they had a rodeo type thing that they would do, like a pig chase and chase the chicken and jump on the horse and race here. Anyway, one of their activities, I don't know, they just randomly had telephone poles lying around, but they would have a couple guys compete in a race to see who could drag a telephone pole from one end of the arena to the other. And everything was based on teams that pitted against each other and such. So here we go. So, Michael, for you, go ahead.
A high school senior exerts a force of 570 newtons as he drags a telephone pole 1,200 newtons across level ground. The constant is 4.70. By pulling on a rope angled at 38.5 degrees above the horizontal, find the acceleration of the pole.
All right, so first things first, we need to draw our free body diagram. I should start by drawing the pole, the telephone pole. How should I draw it?
Skinny box.
Skinny box, okay? That's my telephone pole. And then I need to draw a bunch of arrows, which represent all of the forces. What's one force that acts on the telephone pole? The weight acts straight down. How will I find weight?
That times gravity.
Mass times gravity, normally. Do we know the mass of the telephone pole? What do they tell me about the pole? It weighs 1,200 newtons, right? Newtons is not a measure of mass. That's the weight. I didn't have to find the weight this time. They actually gave it to me. So the last couple of problems have given us a mass in kilograms. We've had to multiply by gravity to get weight. Here they just gave us the newtons, so they gave us the weight. All right? And normally, class, if there's 1,200 newtons down, there's going to be 1,200 newtons up. Now, there's still going to be an upward force. I just don't know how much it is. Because of Michael, or whoever the high school senior is. Michael's like, I could pull way harder than 570 newtons. That's wimpy guy. I got a B. But anyway, whoever's pulling on this telephone pole, trying to drag it across the arena, is lifting slightly upward. Because the applied force here, which was 570 newtons, is somewhat upward and somewhat forward. All right, any other forces in play? Friction force acting against. There's your free body diagram. We've seen a few of these now. Do you feel like for homework later on, for instance, you'll be able to put together a free body diagram similar to this? Again, if the force is a horizontal force, then you don't have to worry about x and y, it's just x. If he'd gotten down at ground level and lugged, it would have been bad for his back, right? But he could have done it, right? Well, here he's not doing that. Instead, he's just pulling at an angle, like the sled problem. I can't find the normal force yet, though. I need to go ahead and split this into the x and y components. The angle, it says, is a 38.5 degree angle. Use that to find applied force in the x and applied force in the y. Once you got your two components, check your answers. Got them? Got them? Got them? All right. Now, once you have these components, class, we know all we need to in order to find the normal force. At your seats, find the normal force. Once you've got it, check your answer. once we know the normal force class, we can find the, and that's the only reason. By the way, if they said that he was dragging this telephone pole across a frictionless surface, listen, if he's dragging across a frictionless surface, I'm not wasting my time getting the normal force. The only thing I need that for is friction. But there is obviously some friction. At your seats. All right. Now then, the ultimate question says, what is the acceleration of the pole? What is my equation that relates forces and acceleration class? F equals ma. So if I want to find A, I need to divide F by m. But not actually the force that's applied, but rather class the, what's that key word? Net force, resultant force. Or we could say the sum of the forces in the x. What is the sum of the forces in the x?
48.85.
Anyone else have that? 48.85 blah, blah, blah? Sum of the forces in the x? Again, all we're doing is taking this, which is x, and this is which is. Those are the only two in the x, right? Nothing else is in the x. Only these two counter each other. Applied force in the x. By the way, what if friction was greater? It wouldn't even move. It's not going backwards, right? Friction is never going to drag something backwards, right? But you're not budging it. It's not, or if it had been moving, it's slowing down now. But if it was starting out stationary and you don't apply as much as the friction is, it's just not moving at all. Make sense? But it is moving, okay? It's accelerating, in fact. Now we need to divide that number, which I'm going to put into the memory, overwrite an existing one if you need to. We need to divide it by the mass. Thoughts?
1,200 divided by 9.8.
That's not the mass, exactly. To find the mass, we need to divide the weight by gravity. So divide it by the 9.80 meters per second squared to find the mass, which is? All right, I'm going to put this in, I'm going to overwrite an old memory for that. So, what is the acceleration of this telephone pole across the ground?
0.399.
And is it 3 sig figs?
2.
Okay, so we'll round it off to say
0.40.
an acceleration measured in.
Meters per second squared.
Questions on this? Let me change the problem a little bit. I'll leave that number up there. Same telephone pole, still has a weight of 1,200 newtons. But instead of somebody taking the time to drill a hole through the end of the telephone pole, run a rope through it so that somebody could drag it by a rope, Michael, or whoever the senior is, has to get behind the telephone pole and push across the ground. Okay? So when Michael gets down to push, his arms are making an angle about like this as he pushes on the telephone pole. Now, question, is Michael pushing forward or is Michael pushing downward? Yes. Some of this applied force, and let's just say it's 570 newtons, even though Michael would push harder than that. Some of the 570 newtons pushes forward. Some of the 570 newtons pushes downward. Let's suppose the angle downward is, say, let's just go with it'd be the same as the angle of elevation here. Let's say it's a 50-degree angle. A 50-degree angle, 50-point-degree angle, so we get our sig figs in. So we have some applied force in the x, we have some applied force in the y. Now, What's that going to do to the normal force? It's going to increase it because now you have two forces, weight plus Michael, that the normal force has to counter. Go ahead and find the applied force in the X, first of all. We got a 50-degree angle. We have 570 newtons of applied force here. What do we get?
366.
All right, I'm going to put that in memory, 1. And to find the applied force in the Y. And what do we get? 436.6. Now, the only reason I really need the Y is so I can help figure out with the weight how much normal force is there. So I don't even need to put that in memory. I can immediately use that number, put it with the 1200 to get how much normal force.
1,636.
That's a lot of normal force. But the only reason I care about normal force, class, is so I can find friction force. Now, Michael's trying to push it that way. Friction is working against it. Same coefficient of friction, 0.470. How much friction is there now?
769.22.
Thoughts?
No.
Michael ain't budging that telephone pole. Not with that lousy little bit of force. Well, let's suppose that was Wimpy guy. This is Michael. 1,570 newtons. That should budge that telephone pole, agreed? Let's check it out. Find the applied force in the X. Same 50-degree angle. Yeah. Now how much forward force, class? 1,009.17, blah, blah, blah. Store one. But by increasing his forward force, he's also happening to increase his downward force. Yeah, we also have to find his updated applied force in the Y. Oh. Yeah, what do we got? 1,202, which means, what's the normal force now?
2,100.
Yeah, it pretty much doubled the weight of this thing. And so, how much friction force is there?
1,129.264.
Now, remember last time it was about 340 compared to 770? He had almost double the friction resisting him. It's not double. He's really close to moving this thing, right? He's almost there. Does that make sense? Here's a question. How much force would it take? Well, obviously more than 1570, right? Well, let's try another number, Michael.
2,000.
Go to 2,000. An even 2,000 newtons. All right, now how much of that's in the X?
1,285.
I hate sine instead of cosine, my bad. He's up to 1285.5. Okay? But that also increases the downward force on the telephone pole.
1,532.
1532, which increases the normal force,
2,732.
which increases the friction force.
1,234.
Woo! Good guess. He has about 1.5 newtons more. So this thing will accelerate. Now, if the sum of the forces in the X is 1.1 newtons, and the mass was, hold on, 1,200 divided by 9.8. That's right, it was the 122.4. Is it accelerating very quickly? No. He is getting 0.0089 meters per second squared acceleration. It is not doing much at all. All right, but he needs 2,000 newtons to get it to move. Big difference, pushing versus pulling. Do you see how the math worked out here? All right, questions on this? All right, your homework for this evening is to complete a handout, and you're going to do just 2 problems that are going to look similar. One time there's a horizontal force, the next time there's a pushing downward force. Okay, so we've got a horizontal force the first time, then we've got a pushing down force. Also, make sure you study over the terms that I taught yesterday. We reviewed a little bit today. Make sure you keep up with those terms. There's not a lot in the chapter, but you do need to know the different types of forces, right? So, which force always acts straight down, class? Weight, right? The force of weight. What is the upward supporting force by a surface? The normal force. What's a force through a chain, rope, string, other connector? Tension. What do we call the force that always resists motion as it slides? Friction. What do we call the single force that shows the net force or the outcome? The resultant. What if we wanted to cancel everything with a single force? Remember what we call that one? The equilibrant. Good, the equilibrant. And if all the forces cancel and there's no acceleration, we have what we call 2 words? Translational equilibrium. We're assuming that it's not going up and down. So we're always assuming translational equilibrium in the y. But in the x is where we're looking at. In each case, we've been trying to see, do we have that translational equilibrium? All right. When the bell rings, you'll be dismissed. Have a wonderful rest of your day.